Okay, I guess that you're watching the presentation already. So I will be presenting. I think it's kind of curious that we in this session we are sharing so different, such a different application of exactly the same technology. So first of all, as I will be um, presenting a case of ammonia recovery, I would like to remind you of the importance of ammonia. Ammonia is a very versatile compound with a lot of different industrial applications. In terms of volume, the primary use of ammonia is the production of nitrogen-based fertilizers, which are essentials in agriculture and actually I would rather say for life, for human life. But besides that application, ammonia is also used for refrigeration, for the textile industry, for the pharmaceutical industry, obviously for household and industrial cleaning products, which is the first thing that probably comes to our minds. It's used in the pulp and paper industry, for explosives, for water treatment, metal processing, for the petroleum industry, and for a lot of many other applications. So it seems quite obvious that as wastewater, I guess that you know that has a considerable a high rate of nitrogen content in the form of ammonia. It could be interesting to use it as a source of ammonia by applying new technologies. Um, I would like to remind also which is the conventional ammonia production process. There are other ones, but the one that's most used currently is has more than a century. It's the Haber-Bosch process. In this process, we get nitrogen from the air by a cooling process, and hydrogen, which is usually uh, valorized from natural gas. The proportion obviously is 1 to 3 by volume, and then by applying a high temperature with an iron catalyst, we produce the ammonia and some gases that are recycled to run the process again. So what's important about this conventional process is that it's using natural gas and a lot of thermal energy in the process. So considering the evolution of energy prices and also the evolution of gas prices in the last years, it is quite obvious that this process, this conventional process, uh, means a problem. Actually, the percentage of worldwide energy consumption for ammonia production is significant due to the large scale of ammonium production globally, mainly for agriculture, for fertilizers, but not only. According to estimates from the International Energy Agency, the ammonia production accounts for almost 2% of the world's total energy consumption. There are other estimates that say that it's 5% of the energy consumption in the European Union. Uh, some more figures. In 2021, the global ammonia production was estimated as more than 600 uh, exajoules worldwide. So, a bit of context. I already introduced the wastewater treatment plant of Rincón de León in the first presentation, so I will not stop in this slide for a lot. But what's most important is what I also mentioned is that in the sludge line in the wastewater treatment plant of Rincón de León, The water sludge is sent to be dried and incinerated at CEMEX. And in this process, we also have a reject current with an ammonia-rich flow. Um, so, an overall view of the process and of the within the flow in the wastewater treatment plant shows that uh, after the sludge drying, we get the reject, the drained water, and we will be using this low temperature evaporation process, this CEVAP process, to produce ammonia, which will have two main applications, intended for two main applications. One of them is producing fertilizers, and for that, we have collaborated with a local fertilizer producer, Medifer, and the other one is the NOx removal, the NOx abatement in the cement plant of Cemex. So actually, there are 2 points in which we have a current reach in terms of ammonia. One is after the mechanical dry, drying of sludge at the wastewater treatment plant, and the other point is in at the CEMES plant, in which we have this drying process using waste heat of the concrete production. Um, both of them, both in both cases, we have a similar order of magnitude in terms of ammonia concentration. But we finally decided to run the pilot using the CEMEX reject water. As at the cement plant, we have the waste heat that would decrease OPEX. And it would also mean that the ammonia would be used on site for the NOx abatement. A bit more in detail, the cement production plants requires roughly 2.5 cubic meters per day of commercial ammonia for the abatement of NOx in the kiln emissions during the cement production. Um, the usual ammonia concentration in commercial solutions is something around 25%, that is to say more than 200 grams per liter. Keep this figure in mind, please. And the process is actually very similar to that in diesel cars, because it's actually the same problem. Is um, ammonia together is mixed with the NOx current, and then by using a catalytic reduction, um, uh, we get to transform this NOx in nitrogen in the avoiding the pollutant emission. Well, we have already seen how the CEVAP technology works. It's a simple evaporation process with low temperatures, usually between 80 and 90 Celsius degrees. As it has this low temperature requirement, it can be driven by low grades waste heat. Another advantage is that it uses replaceable cartridges, which means that at least in theory it has a low maintenance cost, built with plastics, easily scalable. And in the case of the pilot in Alicante, we use actually the same unit that was used in the pilot previously presented, which has a capacity of 100 liters per hour. meaning 200 liters per hour of feed. I would very quickly like to mention that this low temperature evaporation technology has many other uses for brine valorization, for seawater salination, for black liquor concentrations in wastewater treatment, for the concentration of heavy brines, and finally the one that is more related with what we are presenting right now with the for Greek water production and for mineral recovery. As long as we know, it had not been applied directly to ammonia recovery previously. Well, this actually this figure has this image has already been presented. So I would like only to highlight a couple of differences. Uh, First of all, in our case, uh, the stream of interest will be the condensate stream, differently from the case previously presented. And then, as for the heat source, even though as I have already mentioned, the cement plant has waste heat available due to the location in which the plant was set. We had to use a hot water boiler during the pilot. So in our case the heat source was a hot water boiler for the test. So well, this is how it looks like. It's this pilot plant is quite small. It's something like 4 square meters of in area, 2 meters height, and it was located in the wastewater treatment plant for convenience reasons, very close to the mechanical sludge the watering union, even though the water that was finally used to feed the system came from the cement plant of Cemex. So the first test we conducted with pilot plant were batch tests at different temperatures and basically what you see here is that the results are very similar no matter the temperature we use. In terms of concentration, the ammonia concentration in the feed and in the condensate and in the concentrate is very similar. The only difference actually is the flow. That is to say, the time required to get a certain volume. We operated the pilot plant in a partial vacuum condition, 200 millibars. At the initial pH was around 9.5, and the system does not allow us to take samples other than at the inlet and at the outlet of the plant. Well, as you have seen, we are in this batch process. We are not able to increase the concentration of ammonia at the outlet of the system, no matter the temperature. So we decided to run the process in loop, on a cycle, and also first of all we also decided to change the equilibrium point, the pH point, to shift it to more than the equilibrium point between ammonia and ammonium, which is 9.5 roughly. So by using sodium hydroxide, we shift the pH to 10.5 in order to get more ammonia instead of ammonium. Um, so with this, the result was that we were able to go from an initial ammonia concentration of 750 ppm to more than 3000 ppm. That is to say, we multiplied the initial ammonia concentration by almost 4. And we were able to reduce the reagent concentration to less than 100 ppm. You see here that once again, we in the graph in the middle, you can see that at higher temperature, we have a worse result. We are not sure of the cause for this, but it seems that the temperature was not stable, and also as this high temperature mean higher energy consumption, we finally decided to discard this option. Finally, while keeping this higher pH, we also decided to run the process in loop. And for that, we introduced the output of the first batch as in the feed, and we kept the system recirculating during more or less 8 hours. With this, in this table, you can see the results of this. We were able to get a concentrate with 5,000 ppms, which is much higher than the initial result, but obviously it's still far from the commercial solution of 25%. We got a recovery rate of more than 40% of the initial ammonia. And obviously, during this process, we got a much a reduced volume of product. So with after 8 hours, the initial volume of 900 liters was reduced to only 100 liters of condensate. There were some losses of ammonia we were not able to quantify in the concentrate as they were in the shape of vapor. So as conclusions, the ammonia concentration of condensate and concentrate remain similar, as we have said, regardless of the experiment temperature, only the flow changes. Um, the CEVAP process achieve an increase of 1.4 concentration of the ammonia in the feed solution. By adjusting the pH, we were able to increase this concentration to get close to a factor of 4 at 85 Celsius degrees. And by changing the process to a continuous recirculating experiment, we got to increase the initial concentration by a factor of 6 in 8 hours of operation. So, as conclusions and next steps, we aim to perform an evaluation of the economical and technical viability of the full-scale implementation of the CEVAP process at the cement plant of Cemex, considering the available waste heat of the cement production, the capex and opex of the system, the long-term ammonia concentration variability, because we know that actually, depending on the sludge drying operating conditions, ammonia concentration can change along the year. We also need to check the usability of this low concentration ammonia we are able to get for NOx abatement. And finally, on the positive side, also the impact on other problems currently that we currently have at the sludge drying facility due to the ammonia presence. Um, on the other hand, we should also perform a benchmarking of this solution, CEVAP, against other available technologies for ammonia recovery, such as stripping, absorption, chemical precipitation, ion exchange, or membrane systems. So this is it.